Section 2.6 Jointly Distributed Random Variables. The objective of this video are to define joint and marginal probability mass function and probability density functions. Also, calculate joint and conditional probabilities. Consider a population with several attributes, like, for example, the student height and the student weight. We may think that they are related. Now, these variables are said to be jointly distributed and can either be jointly discrete or jointly continuous. For example, if you divide the height that is in foot in between ranges from 4 to 5, 5 to 6, 6 to 7, or higher than 7, and the height also in ranges from 100 to 120, 120 to 140, and so forth, and we put the frequency of students in between those ranges in this table, so we are going to have a discrete table of frequency. So remember, in this corner we are going to have the total number of people. On the other hand, if we just do not arrange in ranges but have the plain weight and height, so we can organize the weight in the horizontal axis and the height in the vertical axis, and we are going to have a section of dots that are representing the pairs of height and weight for each person. So in this case, each dot represents a person, and they're real numbers, and it could take any value for weight and height. So this is a continuous. Okay, jointly discrete random variables. Consider the following case. So we have a population of male and female, and some of them are right-handed and some of them are left-handed. So the total population is 100. So in total, and these are the total, remember the marginal values represent the total. So we have 52 male and 48 female, right-handed in total 87 and left-handed 13. Now for this population, going to name this as X, right or left-handed, and Y will be the gender, male or female. Now this is, remember, this is called a contingency table, and the useful of a contingency table is when we divide by 100 the total population, so we obtain a probability table. So the values now add to 1, either the row or the column or the joint probabilities. So these are the intersections that represent the joint probabilities. Now in a more formal way, so remember, this is the X and this is the Y. So the joint probability, which is the probability of XY pair, is given by the probability of X being to X and Y being to Y. So the lowercase y, X and Y represent a particular value. So in this case will be male, female, right-handed or left-handed. So let's say, for example, that we want the probability that X is equal to right-handed and Y equal to female. So we have a joint probability, and in this case right-handed and female, the intersection is 0.44. Remember the property, all the probabilities have add to 1. So if we sum the probabilities of xi, yi, and we do the sum in I and j, so this probability should be equal to 1. So that means if we add everything in this square region, it would add to 1. Now remember, marginal probability mass functions. So the marginal values are the ones that are on the margins. So one of those are going to be the marginal values for our x variable, and some of them are going to be our marginal values for our y variable, so x and y. Now, the marginal values for x, it will represent the sum over all the y values. So we are doing the sum over the y values for x, so we add in this direction. For example, the probability of being left-handed is the sum over this column, and that will be equal to 0.13. On the other hand, if we want the marginal probability for y, we have to add over the x value, so that should be x. So for example, if we want the probability of being female, we have to add over the row values. In this case, the probability of being female is equal to 0.48. Now, different story is if the variables are continuous. So if the variables are continuous, we have integrals instead of sums. So we are going to have probability mass function. So I represent that in a plane. So we have our two variables x and y, and imagine the joint probability of x and y is a surface on over the domain which is given by x and y. Now, if we want to know, for example, what is the probability of x being in between a and b, so x being in between a and b, and y being in between c and d, so that will be what's the probability of being in this region. What we have to do is add all the values in between these regions. So how do we add the values? Well, that's the integral in the continuous way. So what we have is that we have to do the integral from a to b for x and from c to d for y. Remember that probability is density function. In the case of one variable, they have always be equal to 1 when we integrate over the whole domain. When we have the joint probability of these two functions, it should be the same thing. The integral from minus infinity to infinity of the integral from minus infinity to infinity of f of x y dx dy should be equal to 1. Now, how do we do or compute the marginal distributions for x and y? Now our domain is continuous, and instead of doing sums, we do integral. So the marginal probability for x, so we have to integrate over y variable. So we integrate from minus infinity to infinity of f of x y dy. So when we integrate over the y variable, we are eliminating the y variable from our equation. So that's why the resulting function is a function of x only. So what are we doing in this case? We are integrating over dy. So we are integrating over dy. So it's like compressing this into a line. So the resultant expression f of x, it will be something like that. So this is x and this is f of x. On the other hand, if we want the probability density functions for y, so we have f of y equal to the integral from minus infinity to infinity of f of x y integrated over dx. So what we should integrate is over dx. So we are going to compress our function, and the resulting function is a function of y only, so I'm going to write this is y and this is f of y, and we are going to have one function, and this integral should be equal to 1, the integral of f of x from minus infinity to infinity of f of y, equal to 1, and in a similar way this integral, it should be also equal to 1, the integral from minus infinity to infinity of f of x should be equal to 1. This is dy and this is dx. Okay, let's have a look of this concept into an example. So we have a washer. So a washer, it has a thickness, and the thickness we are going to call it the variable x, and the diameter, the internal diameter, we are going to denote it by y. Now when we manufacture the washers, we are going to have a jointly this probability density function that is given by this value. So is equal to 1/6 of x plus y if x is in between 1 and 2 and y is in between 4 and 5 and 0 otherwise. So if I plot the domain for x and y, so we are going to have nx, the thickness, and this is not a scale, so we have the thickness and the diameter, and so the region in yellow is the region in which the probability density function is different from 0. All around is equal to 0. Okay, so the question is, what's the probability of the thickness being in between 1 and 1.5 and the diameter in between 4.5 to 5? So what's the probability of being in this region? So what we have to do is integrate. So the probability of x being in between 1 and 1.5 and y being in between 4.5 and 5 is equal, so we have to integrate for those regions. We have to integrate f of x y dx dy, and x is going to be in between 1 to 2 and y is in between 4.5 to 5. So now we have to replace by the value of the integral. So the integral function from above is 1/6 of multiplied by x plus y, 1/6 multiplied by x plus y dx dy, and the limits are 1, 1.5, 4.5 to 5. I'm going to develop this in a fast forward way, so you can follow at your own pace. So the answer is the probability is equal to 0.25. Let's compute some marginal probabilities. For example, compute the probability of the thickness of the washer, that is, the probability of f of x, and is equal to the integral from minus infinity to infinity of the jointly probability density function f of x y, and we are integrating over dy, so the variable y is cancelled. That is, we are integrated in that direction. So our variable in reality has only values different from 0 in the range from 4 to 5. So f of x is equal to the integral from 4 to 5, and f of x is 1/6 of x plus y dy. Developing this integral, we have that is equal to 1/5. The integral of x is y plus the integral of y is y squared over 2, and the limits are in between 4 and 5. Once simplifying, we obtain that f of x is equal to 1/6 multiplied by x plus 9 over 2. So this is the probability density function for the thickness of the washer. We can observe that that's a linear function, and the range for x is in between 1 and 2. So we have a straight line whose only possible values are in between 1 and 2, and the equation is given by 1/6 multiplied by x plus 9 over 2.